Okay, so a very basic question. Sounds rather simple. You might think we know the answer, but we don't. Is what are all the non-trivial symmetries of nature as we currently understand her? And by that I mean general relativity and the standard model of physics. And by non-trivial, I mean a symmetry that has some predictive power, like energy conservation. You put in some amount of energy in the beginning of some situation, it changes form. At the end, you get the total amount of energy is the same. Now, we actually know energy conservation is one symmetry. We actually know that there are infinitely many symmetries in nature which control the interactions of particles, people, everything that we see around us. But we don't know exactly what they are. And I would say that the theorists are greatly behind on their homework, because we can write down the theory on a piece of paper, but we have not yet understood everything there is to say about the laws of physics as we have already confirmed them, and what kind of experimental consequences they have. Now, a lot of recent progress on this subject, and as the talk progresses, you should see that this question is actually both more difficult and more interesting than you might have imagined. So recent progress on this question involves the discovery of a complete mathematical equivalence. I don't mean analogy, I mean a complete mathematical equivalence between three things that experimental and theoretical physicists have been studying for more than half a century without realizing that they were describing, discussing, measuring the same thing that had been in different languages. And these three things are the asymptotic symmetries, which is a concept which pioneered by Bondi, Vanderburg, Mesner, and Sachs in the 60s. The so-called soft theorems in quantum field theory, which are really even older than Weinberg in 1965. And they're a property of Feynman diagrams in quantum field theory, and they're employed mostly in computed cross sections in colliders. Well, in any application of quantum field theory, you need to understand them. And then there's something else called the gravitational memory effect, which was predicted, follows from Einstein's equation in 1974, has not yet been measured, but a recent review article on the subject says that LIGO is likely to be able to see it in the next 5 years or so. And certainly advanced LIGO will get good information on it. And other experiments like the pulsar timing array and so on may also be other ways to measure it. So again, I'm not talking here about any new physics. I'm talking about new discoveries and new understanding of old physics, which nevertheless lead on to both new, we'll see, lead to both to new experimental predictions and to new directions for going beyond what, new theoretical directions for going beyond what we already understand. Okay. So the first discovered, oddly, usually gravity is the last thing we understand, but for some reason, in this particular triangle of equivalences, the gravitational, there's a triangle of equivalences for every force in nature. And in fact, there's an infinite number of triangles for every force in nature. And for some reason, gravity is usually the most complicated. But in this particular context, things were first understood in the context of gravity. So this triangle involves something called the BMS asymptotic symmetry, the leading soft graviton theorem, and the gravitational memory effect. So let's start with the symmetry. What are the symmetries of general relativity? So this is a subject in which general relativists had flip-flopped and come up with many contradictory answers for the last 100 years. Now, many people, when they teach general relativity, including myself, say that the basic symmetry of general relativity is diffeomorphism invariance or coordinate invariance. It doesn't matter. You can define your system using any kind of coordinate set, and you should get the same prediction for any physical experiment. However, there are other formulations of general relativity, famously one due to Reggie, where you work in a kind of lattice of triangles and lengths in which you don't explicitly have coordinates, you just sort of construct the geometry physically. And so those trivials, most of those symmetries that I've just described, coordinate transformations, are trivial symmetries. They don't have any physical predictions. They're sometimes referred to as redundancies of description. You can describe things in a different way. That's not very interesting. It doesn't lead to a conservation law like like energy conservation. And any given physical theory can have many different ways, many different descriptions, which have different amounts of redundant symmetries. A simple example is pure free electromagnetism. We have electromagnetic gauge invariance of usual description, but we can do a duality transformation to a magnetic frame. And then we have magnetic potentials, and they have an unrelated redundancy. So the redundancies and descriptions are not the things that we want to understand. So now in special relativity, Poincare symmetries lead, via Noether's theorem, to measurable conserved charges such as energy, momentum, and angular momentum. For example, energy conservation is related, through Noether's theorem, from time translation symmetry, under which time goes to t plus the constant. And however, interestingly, this of course is a coordinate transformation. I've written it here very explicitly. T goes to t plus a constant. But the time translation symmetry, I would say, is a non-trivial symmetry, leads to a conservation law, energy conservation, whose effects we measure. Now, way back in the early 60s, Bondi, Vandenberg, Mesner, and Sachs had the idea that in general relativity, you're allowed to do much more than just the Lorentz transformation within translations of special relativity. You're allowed to consider general coordinate transformations in which the first set of coordinates is basically arbitrary functions of the second set of coordinates. And that's general covariance. And so at the starting point of the usual form of general relativity is this huge symmetry group. And somehow, so they thought, there ought to be some limit in which this huge symmetry group of general relativity reproduces to the Poincare group, which is translations and Lorentz transformations and their associated charges. And they were pretty more or less mathematicians, and they wanted to set this up carefully and try to understand exactly how you reduced from this infinite dimensional group to the finite 10-dimensional group of Poincare symmetries, which they thought would set in if you had an isolated gravitating system like a sun or a black hole at very large distances. You should just get Einstein's general theory of relativity should reduce to special theory of relativity. Now, the answer was a big surprise. And the answer has bothered people for practically up until the present time. And now we think we understand how to make sense of it. but it wasn't what they expected. Let me tell you the key ideas of how this is set up. This is a picture of an asymptotically flat spacetime. In the picture here that I'm drawing, it's called a Penrose diagram. And it's a picture in which time goes to the future, space goes to the left and the right, and light rays go up at 45 degrees. And in this picture, there are 5 kinds of infinities. Future time-like infinity, where you and I will go to if we never die. Where we come from if we live forever, past time-like infinity. Spatial infinity, where if you follow an arrow in an infinite distance, at infinite speed, you get out to spatial infinity. And then there's null infinity, where light rays go to, future null infinity, and past null infinity, where they come from. Now, so they introduced the notion, actually Arnaud, Deser, and Lisner, already in the 50s, but Fosdick, Hester, and Sachs used this, and they introduced very carefully, mathematically, within the theory of general relativity, they introduced the notion of an asymptotically flat spacetime. An asymptotically flat spacetime is one which, far from strongly gravitating sources, the space is nearly flat. So space is nearly flat in this room. I mean, of course, there's some dark energy, but very, very nearly flat in this room. And they just saw this beautiful image of the black hole, M87 star. Space is very highly curved from that. So we are in the asymptotically flat region relative to these strongly curved regions of the universe, where, like around the black holes, are just strongly gravitating stars, and so on. So in this region, they expected somehow to see an action of the Poincare transformations familiar from special relativity. So how did they expect to get that? Well, they defined something called an asymptotic symmetry. So they have to specify some boundary conditions out here. And this was also the time at which the meaning of gravitational waves, which we've recently seen, was really spelled out in a precise way. What is a gravitational wave? And it's some small deviation of a flat metric. And they spelled out exactly what kind of boundary conditions the geometry should obey out here in order to be, quote unquote, asymptotically flat. And they were interested in all the general coordinate transformations, which preserve the boundary conditions, divided by the ones that act trivially on the boundary data. So there's the ones that do nothing at infinity, and the ones that act non-trivially at infinity, and those should be, they hope that would be the Poincare. So clearly, if you take the boundary at infinity and you time translate it, or you space translate it, or you rotate it, you preserve these boundary conditions. But that was not what they got. They got a very interesting infinite dimensional group called the BMS group. And the BMS group allows for not just global time translation, where time is translated everywhere at the same rate at infinity, but there's a symmetry in which you translate time differently at different points, at different angles along the sphere at infinity. So at infinity, you shift time, the retarded time, at infinity by an arbitrary function of the angle at infinity. So a special case when f is a constant is an ordinary translation. The general case is called a supertranslation. And by the way, they used that word several decades before it started getting used in the subject of supersymmetry or something else. So we stuck with it. So these are allowed by the boundary conditions, but they act non-trivially on the outgoing data. So they're not trivial. they're allowed, they preserve the asymptotic form of the metric, but they act non-trivially on the outgoing data. So suppose you have so you could take a picture, an example, we have two photons, and then you do a super translation, which vanishes at this angle, but translates by a year over here, and you get something different. So we would like to think that we can physically tell the difference between these two things. Like if a pion decays into two photons, we can tell that they came out the same time and came from the same place. So this is clearly a physically different situation. And you can't, there's no sensible way to say that, that this particular coordinate transformation is trivial. So people didn't know what to do about this. Many people tried to impose an auxiliary boundary condition that would eliminate this freedom. They thought it was some kind of tricky gauge freedom that they hadn't understood. It should be redundant. And now there's also the question of how the data on scry minus is, in the past, is tied to the data on the future. What BMS analyzed was only what happened in the future. Now, another example of a non-trivial symmetry is a boost. So a boost, clearly non-trivial. You have, say, a black hole sitting there of energy E, you boost it, you change its energy. It's a coordinate transformation, but clearly it's not a trivial one. It changes the energy. We wouldn't want to identify the two states with the energy. But we know that in a physical situation, that if you boost something in the past, in the future, it should go to the boost of whatever you had in the future before you boosted the thing in the past. So there should be some linkage between the action of the symmetries in the past and the action in the future. And nobody could understand how to do that. It seemed impossible to link the super translations in the past and the super translations in the future. And that was the problem that was solved about 10 years ago. And you have to really understand in detail this kind of how here you have to understand in detail spatial infinity. And it turned out that within this general relativity, there were some very wrong conceptions about what the structure of spatial infinity is that was cleared up in a seminal 1992 paper of Christodoulou and Kleinerman, in which they showed that the kind of structure that people had thought, it's a mathematical physics monograph in which they also proved local existence and neighborhood of general relativity equations and neighborhood flat space. And along the way, they cleared up this business of what the structure looked like 30 years after BMS, what the structure looked like to spatial infinity. But they didn't go back and ask any questions about BMS symmetries. But we used that, and we showed that a rather strange thing, that if you do a super translation in the future, and you do a super translation in the past, which is antipodally related. Like if I super translate by 5 minutes on the South Pole in the future, on null infinity, I have to super translate by 5 minutes on the North Pole on past null infinity. In other words, at the opposite side of the sphere. So there's an antipodal matching, which can and has been derived in other means, which actually is a conventional symmetry in the sense that it implies conserved quantities, and there's associated charge that generates these symmetries, and that charge commutes with the S matrix. In other words, everything you would want a symmetry to B. So yeah, just say it that way here. So if B generates these funny BMS super translations, we've shown that they commute with the S matrix. And that means, for example, that if you have a given in state that scatters into a given out state, you act on that with a BMS transformation, it will transform into the BMS transformation of the original out state. Okay, so these are true symmetries of GI. You can we're going to talk in a moment about how you measure them, but not all of them. Okay, so symmetries imply conservation laws. Like for F as a constant, the conservation law is the total incoming energy is equal to total outcoming energy. But more generally, using that symmetry I just served, the antipodal BMS symmetry, you can show that the integrated all over all advanced times, all the energy that came in through some angle is equal to all the energy that goes out some angle. Now, you might think I'm crazy because suppose I take an electron and a positron, I send them in like this, they scatter at right angles, and they do that. Then it seems like I've got energy coming in at this angle and nothing going out at the opposing angle. What happens is, if you do that, the conservation laws, and in this case, the Maxwell equations, electromagnetic process, require that there be a burst of Cherenkov radiation, which does go to the opposing end. And indeed, if you measure it, you'll find that all of this works. So, in fact, it's always true. And yeah. Okay, so there are an infinite number of conservation laws in general relativity. There's one energy conservation law at every angle. Okay, so now I'm going to turn to a completely different topic. Seems like a completely different topic, but I'm going to show it's the same thing. And that is the so-called soft theorems. Or let me pause and ask if there are any questions about what I've said so far. I don't know if there are any questions.
Examples, I guess, they are actually talking about the initial phase radiation and final phase radiation. What are you saying about this term about light? Terms of supposed to be very simple.
Well, I mean, if you solve the Maxwell equations, Maxwell would have agreed with this, right? So if you solve the Maxwell equation and you have the particle go off this way, you'll find that there'll be energy deposited in the opposite. Yeah, really, because I'm talking about gravity here. Really, I shouldn't be talking about gravity. So let's take two black hole scattering, which something people measure now. There are two black holes which scatter, and you'll have a burst of gravitational radiation that goes along the line of the incoming particles. Yeah.
Nothing came in at the right thing.
Yeah, good point. So you have to be careful about that the energy in general relativity has a term which is linear in the metric fluctuation. And that term will be negative and will cancel the stuff that goes out. Very good question. Yeah.
So you mentioned that in setting up BMS symmetry derivation, you have to essentially choose some the boundary condition, right? And your study would be the invariance of the boundary conditions. Is there a guiding principle for what boundary conditions we choose, and or is that sort of backwardsly informed by board identity, therefore we should expect a symmetry, therefore we sort of import the boundary conditions?
Yeah. So, this is an example which really illustrates the fact both that physics is an art, not a science, and that artists do great things. Now, so in fact, BMS, they're all of these things. They talked about the ratio of allowed versus trivial. And both of these are a little bit fluffy concepts. Now, they made them mathematically precise and then implemented them. And once they had announced what the mathematically precise form was, you could go from there. But other people came along later and said, no, that's not the way to. There was also the Newman-Unti-Tamburino group, and there were other, and it wasn't really clear exactly what you were supposed to do. And moreover, this business about the boundary conditions of infinity that Professor Euler and Feynman figured out, that was also somebody came along. This is what the boundary conditions should be in general relativity, and that this was wrong. Almost everything that was said was wrong in one way or another. However, it was all, genius stuff. It was a beautiful, it's a fundamental insight. They got, that's one of the other great things about it. It doesn't matter how many times you get it wrong. It's just how many times you get it right, and that's the last one. And so they did correctly see the very deep point that, and we'll understand this a little better exactly what this means, that general relativity does not become special relativity in the deep infrared, and that there's a lot of structure at long distances in general relativity that is not just the empty flat space of Minkowski space. That I would say originated in this BMS. But indeed, the field suffered from this kind of ambiguity. I didn't know which coordinate system to use, which gauge, we overgauge fits, undergauge fits in. People got awful lot of it right. The thing that is weirdly much more defined, I'm about to talk about soft theorems and Gravitational's equivalent. Nobody ever argues Feynman diagrams are very well defined. And nobody ever argues about properties of Feynman diagrams. And indeed, Feynman diagrams are used to compare anomalous magnetic moments, and they agree, those calculations agree to whatever it is in the system. Maybe they've added another decimal point. So by tying this very powerful intuitive picture that Bonnie Messner Sachs to the computationally powerful but far less intuitive picture of Feynman diagrams, we're getting the best of both worlds. Okay, so here is very precise Weinberg's soft graviton theorem. Yeah.
Just one more question. If you take the limit of the flat space time,
Yeah.
you'll get these symmetries.
Yeah. We take the limit of a flat space-time.
Yeah, like you actually consider Minkowski space.
Yeah, with gravity.
No. Well, let's say you study, you could use your RV light, but you're studying a flat metric. My question is then, do these negative or dependent symmetries correspond to anything? Or
Yes. Yes. I'm going to say in a moment that there are many flat metrics. The vacuum is not unique. And the memory effect is how we know that. It's how we will confirm that experimentally. Okay, so what did Weinberg say? He said, let's take any scattering amplitude, any particles in any theory, a very incredibly simple, beautiful derivation. And let's then add to that scattering one graviton. And let's take a polarization tensor epsilon, and let's take its energy momentum to zero. He showed that that is equal to the so-called Weinberg soft factor, which is a number in momentum space, times the same scattering amplitude without the insertion of the soft gravity. Plus, so notice that we're taking Q to zero. We've got a 1 over, so what is this? This is the sum of the graviton momentum dotted into the momenta of an external particle. At the bottom and on the top, we have the square of that momentum dotted into the polarization tensor. And you take this ratio, you sum it over all the external particles, that's a number. And so the soft limit is just a number times the amplitude without the soft insertion. And then there are corrections to that. Okay, so this is a very powerful and universal formula. And I think it was largely regarded in quantum field theory texts as it's just kind of a technical formula that you use to help make things work. Now, but in fact, it's exactly the same as these antipodally identified. Not, you can't get it from BMS, but if you take the BMS supertranslations on the top and on the bottom, you antipodally identify, you have a symmetry of the S matrix. And then if this is zero, this must be true for any in-state and out-state. And after many pages of writing things out in different rotations and transforming from different formalisms, you find that this formula is identical to this one. So if we hadn't known about Weinberg's soft graviton theorem, and once we know about that typical matching, we could have derived it. And conversely, if we hadn't known about BMS symmetry, we could have derived it from Weinberg's soft graviton theorem. So they are exactly the same thing. Now, what do we learn from this? So I want to say that in general relativity, the vacuum is infinitely degenerate. There is not a unique vacuum. Classically, we can understand this by saying that G mu nu is not preserved. G mu nu equals eta mu nu. If we act on this with a super translation, if we act on it with a Poincare transformation, we get back G mu nu is equal to eta. The Poincare transformation is one of the BMS, is an element of the BMS group, but there are many more in the BMS group, the super translations, and they don't preserve the metric. And when you have a symmetry that doesn't preserve your ground state, the words that you say are the symmetry is spontaneously growing. Like you have a ball on a circle. It's a point. The system has a symmetry, a circular symmetry, but the ball spontaneously breaks the symmetry. At the quantum level, we can say, since we take a soft graviton with zero energy, that commutes with a Hamiltonian, but doesn't commute, it's got spin 2. So it doesn't, it changes the angular momentum. So if we take some state, we take a vacuum state, we act on it, we get a new state by acting on it with a soft graviton. We get another state which is still the vacuum in the sense that it has zero energy, but it has angular momentum which differs by 2. And it's not sensible to identify 2 states which have different angular momentum. And that if you do that, angular momentum can't possibly be conserved. And this was known for 50 years as the problem of angular momentum in general relativity. People were unable to show in general relativity that because expression for angular momentum is not manifestly important, so they were unable to show that angular momentum was conserved. And the reason they were unable to show it is that they were assuming that the vacuum always had zero angular momentum. And when you account for this, then angular momentum is perfectly conserved. And there is no problem of angular momentum in general relativity. It's just that the vacuum carries it. And more physically, if you did an experiment in general relativity and you kept track of all the particles that were coming out, you would think, and you didn't count for the fact that at the end of the day, what you were left with, and the amounts that were going on, you would conclude that angular momentum conservation is viable. Okay, so it's fascinating. I asked Weinberg about what he thought about the fact that BMS discovered the same thing essentially that he did, essentially the same year. Was that a coincidence or what? His response was, well, you know, ideas percolate through the community. At that time, what everybody wanted to do was to use symmetries to push them to their ultimate power, and they were doing this in different fields. Okay, now I'm going to go for a second topic change, the gravitational memory effect, which really I should write their name. The first mention of it is in an even earlier article by Gibbons and Hawking. They just have a paragraph on it. Here's the gravitational memory effect. I think I won't try to explain all these equations here. So at LIGO, they have some mirrors, and when a gravity wave comes through, the mirrors oscillate. But when the gravity wave is done going through, the mirrors don't come back to their initial relative position. There's a DC offset. And what you can show is that a way to understand how this happens, and this can be made very precise, is you're in the vacuum, some gravity waves come by. After the gravity waves come by, you're not in the same vacuum anymore. You're in a vacuum which differs by a BMS supertranslation. And the points are moved around. And if you have various detectors tiling the sphere at infinity, their relative positions will be changed. So a gravitational wave, if you like, can be thought of as a domain wall, which divides two vacua, which differ by a BMS supertranslation. And the shift can be understood as coming from exactly the diffeomorphism accompanying on the sphere that accompanies the, here I've written it out explicitly, that accompanies the BMS transformation. And so if we measure this, and this is, you would have to know, in measuring this, you would know how much angular momentum the vacuum carried in order to see angular momentum conservation in any real experiment. You see it to a very high degree. You would have to keep track of this, and this is how you would see what vacuum you had shifted to if you wanted to verify angular momentum conservation. So this is the experiment, if you like, that measures the experiments that measure these infinitely many conservation laws will all involve memory-like measurements at infinity. Okay, now here's another thing. I love this here. So these papers came out. Well, this was after the discovery of gravitational memory, but they tried to work out the size of the effect exactly. And so if you look at this, I hope you can see it. The difference here, this is a formula for the metric perturbation in momentum space. Here, it's a formula for the change in the metric from the far past on the scribe to the far future. So this side is the Fourier transform of this side. And so these two formulas are exactly the same. But Weinberg was scattering hard particles, electrons or something, and Brzezinski and Thorne were scattering black holes and neutron stars. So they accordingly used capital P, because they were big things, whereas Weinberg used little p. Brzezinski and Thorne, they left the I epsilon prescription, the I epsilon implicit, but otherwise you can see these two formulas are the same. And one is the gravitational memory effect, the other is the photon theorem. They were written a little more than a decade apart, but it was another 3 decades before anybody noticed that these were actually exactly the same formula. And of course, it's a testament to the universality of these phenomena that relativists working on scattered black holes and neutron stars would come up with the exact same formulas as quantum field theorists try to construct the standard model. Okay, so in summary, there's an infrared triangle, these 3 things: the gravitational memory effect, the soft graviton theorem, and asymptotic symmetries, and they're related in very simple and concrete ways. Now, this is just the beginning of the story. So, for example, whenever we have one corner of the triangle, we now have, since we understand how this procedure works, we have an algorithmic way to flesh out the other 2 points. And there are many examples in which we have one corner and we don't have the other corner, we flesh them out. And so here, it happens in electromagnetism, and that's what I'm going to discuss next. And it happens in gauge theory, there's color memory, there's all kinds of, there's subleading soft theorems in QED and in gravity and so on. So there's a whole sort of landscape of interesting things to try to understand here. And we do encounter qualitatively new phenomena and also new experimental predictions. And what time should I go to? Okay. So now let me talk about the electromagnetic case, which you might have thought I would present it first. Sometimes I do. But I'm going to present it. This can be attacked. This can be approached from many different points of view. So I'm going to now attack it from a rather different point of view, and you'll see that how we come to the same conclusion. Okay. Here we have a static charge, electric field goes like 1 over r squared. Now here's what happens if we boost the charge. This is the boosted field, which you can look up in your electromagnetic textbook. But one of the interesting things surprised me when I realized it, though people have been aware of this for centuries. This, if you just take r to infinity, this expression is not single value. Depends on how you get to r goes to infinity. And here is the boosted world line. And if we start at a point here, and we go up to null infinity and then down there, we get this expression. Whereas if we start down here and go up there, we get a different expression, where they differ by a crucial sign. And this crucial sign means that the leading component of the electric field, at the bottom, the leading component of the electric field at the past of the future, at the far past of the future, is not equal to the leading component of the electric field at the far future of the past. They're antipodally related. The value of the electric field here is related to the value of the electric field there, and vice versa. So you can show that this is completely general just from properties of the Feynman propagators, retarded advanced propagators in all the textbooks, that actually what you get when you construct things with Feynman diagrams is always going to obey this kind of somewhat surprising antipodal matching condition. Now, once you know that the fields are antipodally matched, it's easy to construct an infinite number of conservation laws. You just take these f's are equal up to antipodal stuff. So you just take some function on Minkowski space that bears an antipodal relation here to here, and you integrate it against the charge and use the fact that these two are antipodally identified. And for every such function, we get a conservation law. Now, if we take that function to be a constant, then this is just the total incoming electric charge is equal to the total outgoing electric charge. But suppose we don't take it to be a constant. And what I've indicated here is we take this electric field, we take it and we view it as the boundary of a surface, and then we use Gauss's law to integrate by parts, and that gives us an expression for the incoming charges for this one, and for this one we need to go this way, and that sorry, the first was the outgoing, the second would be the incoming. Now we can still integrate by parts, even when we don't, epsilon isn't, this function is not a constant, and then we get incoming charges weighted by arbitrary functions of their angles, plus some strange thing that involves linear in the electromagnetic field is equal to outgoing charges plus another strange thing. So there is a number you can make. You give me a function epsilon on the sphere, and I can make a weird number which involves integrals of the incoming electric field, that involves weighted sums over the incoming charges. Make me any number, and I know for sure that even before I solve the problem, and I don't even care how they scatter, I don't care what their interactions are like. It's a completely universal statement. That I'll get the same number, and there's an infinite number of such numbers, one for every function. And this is just classical physics now. This is already true. And but we see here that the electromagnetic part involved an integral over all advanced time. So when we promote that to an operator, it's going to be a soft photon, and its polarization is going to be the derivative of this function that we chose. Now in quantum mechanics, we should have this, and then we put that back in, and again, we work it all out, and we find that this conservation law that we just derived from the antipodal matching is, again, it's the soft photon theorem. And again, we can reverse the logic and get the antipodally matched charges starting from the soft photon theorem. Now we can talk about conservation laws going to symmetries. We have these conserved charges. What do they generate? Well, they generate large gauge transformations in Maxwell in QED. So these are gauge transformations in QED, which go to angle-dependent constants in infinity. They don't go to 0 to infinity. They don't go to an overall constant infinity. They go constant at future null infinity, and they go to the antipodal related constant in past null infinity. These are true symmetries of QED. And we can, once we know exactly expressions for these charges, we can canonically quantize the theory, and we can see that they generate the large gauge transformations. So that is the meaning. So the large gauge transformations of QED are the BMS transformations of general relativity. And it's an odd thing that the large QED, which has the same phenomenon, it was discovered 50 years later than it was discovered gravity, which would seem to be more comfortable, but that is what happened. And so it's also true in QED that the vacuum is not unique. We can add a soft photon, carries 1 unit of angular momentum. And the vacua classically are characterized by flat gauge connections on the celestial sphere of infinity. And there's also an electromagnetic analog of the gravitational memory effect. And again, okay, so here what I'm saying was before that that I can do a large gauge transformation on the vacuum that has spin 1. I get a different state, it has another soft photon. So in many degenerate vacua with different angular momentum, we could characterize it saying that the quantum vacuum has what's called soft hair. It has distinguishing characteristics from the soft physics in the infrared. So there's a memory effects in all these theories. In gravity, in a way, it's the simplest to think about conceptually. You have there's stuff comes out at null infinity and detectors are moved around. In electromagnetism, they get quantum phases. In Yang-Mills theory, their color gets changed. So if you have 2 quarks at different points on the sphere, they'll have a relative rotation. And we'd like to measure the electromagnetic memory effect. It's kind of like measuring the electric Aharonov-Bohm effect. Not so easy to do because of transients. There have been some proof of concept detectors, but I don't think these people were really making a proposal for something to build. We did make a proposal with some of the people at Brookhaven at electron-ion colliders for measuring color memory. In color memory, what you have is deep inelastic scattering. There's something called a color glass condensate that nuclear theorists believe forms in these heavy ion collisions. There's good evidence for it. And inside that color glass condensate, you have something that approximates classical Yang-Mills theory with a running coupling constant. In a deep inelastic scattering, you have a photon that goes out. The photon becomes a quark dipole, and then it undergoes color rotation and then comes out. And the amplitude is this Wilson loop, which is the size of the color memory effect. And so that's that good chance that can be measured at heavy ion collisions at this new $1 billion electron ion collider. Now you might wonder how this could be measured. And I mean, it's an important point. Why can we measure this in QCD? Because there's no long range fields. And this is it something in the deep infrared? No, it's all about zero energy. Well, you could worry about that already with gravitational memory at LIGO. What happens at LIGO? If you look at the LIGO signal, the mirrors oscillate, and then they don't come back to their initial position if they were on coasters, but they're not on coasters, they're hanging on pendulum. So they swing back. And so if you're going to measure gravitational memory, you have to do it, you have to have a separation of scales. The scale associated with the waveform has to be smaller than the scale associated with the pendulum. And they have that, but it's not very big. It's only like a factor of 3 or 4. And if they didn't have the pendulum there, they would have measured it already. It's that's what's getting in their way. And okay, those guys are magicians. They think they'll be able to measure it. So I believe them. But it looks different. Now those are the implications of this triangular structure for experiment. But there's also a lot of implications for basic theory, which is the thing that I've been mainly involved in. And let me just briefly into transparencies. I mean, the bulk of the talk is done. I'm not going to go at all. We're just going to allude to what kind of theoretical things come out of this. One important thing is for the black hole information paradox. Black hole information paradox comes from the fact that the Hawking quanta that are formed when the black hole evaporates are uncorrelated quantum mechanically with the quantum state of the black hole. But we've already accepted the fact that that's not true whenever you have a conservation law. For example, we don't think that the energy of the outgoing Hawking quanta is uncorrelated with the energy of the black hole. We believe that in Hawking evaporation, nobody's ever questioned whether energy is conserved. We believe that energy is exactly conserved. Therefore, there's a correlation between the quantum states of the black hole and the Hawking. Every moment, energy is exactly. So now we have an infinite number of conservation laws, which we've been able to describe very explicitly. And these enforce an infinite number of correlations on the evaporation process. And an infinite number of correlations is enough to force all the information in the black hole to be copied in the Hawking quantum. It's enough to enforce that correlation. It's enough, but we don't know if it actually does. Okay, so but this looks very interesting, and so this is the soft hair program that I started out with Hawking and Perry a few years ago, and we're still working on. Now, another important application of this is the generalization of the holographic structure found in the ADS-CFT correspondence to flat space. So the very first step 0 in ADS-CFT historically was to identify the symmetries of the conformal theories to the near horizon symmetries of the black holes. That was step 0. And actually, that step 0 was already compelling enough to be convincing that there was a duality, that the near horizon symmetries of the black holes matched the conformal symmetries of conformal field theories in one dimension lower. Here we're in much better shape, except for the case of three-dimensional black holes. The symmetry groups were finite dimensional, so not so powerful. Here we have these enormous infinite dimensional symmetry groups, which, if we're going to have a holographic duality between physics in asymptotically flat space and quantum gravity in an asymptotically flat space in some kind of a field theory, both sides had better obey the same symmetry, otherwise you're completely cooked. But it's very hard to get something on this side that obeys the same symmetries. First of all, it obeys all the symmetries of a conventional 2D CFT, and that's the kind of symmetry that that's the infinite dimensional symmetry we obey most. But there's even more. There's W symmetries, there's translation symmetries. And so it's now, so the basic proposal is that on the basis of symmetries, that if there is a holographic dual of quantum gravity in flat space, it must be possible to formulate it as some kind of exotic conformal field theory on the celestial 2 sphere, which lives at null infinity. I should say that the Lorentz group, which is SO31, is also the conformal group. It's SL2C. It's the conformal group of the Euclidean 2 sphere. So this is a currently very active topic and a subject for a different colloquium. But we've made, just in conclusion, we've made an enormous amount of progress in understanding what quantum gravity might be like in the top-down approach in string theory. But there's also seems to be a gold mine of information in working from the bottom up that we haven't milked for all it's worth to understand how quantum mechanics can be consistent with gravity. And there's a lot to do. So let me stop there.
Okay, yeah, thanks for a very inspiring talk. If you have a couple of questions, let me just say that there's a reception right afterwards. It's about a 2-minute walk away, but there's a carefully designed path to keep you out of the rain. And there are signs and follow people, but it's like 2 minutes away. Okay, so questions? More questions?
Is there an analog of Boltzmann theorem for this?
Analog what?
The Boltzmann theorem for this.
Yeah, there's Goldstone modes. There's massless Goldstone modes for what?
In the case of 3D,
They're the soft photons. They're the canonical partners of the soft photons.
because if you say that the recording is smarter because it is something to be wrong, again, one form symmetry. Is there any
Yep. There's in Goldstone's theorem, you take Goldstone's theorem means to be that there must be for every direction in the moduli space of vacua, there must be a massless particle. That is true in QED, and those particles are. We were discussing this earlier today at the discussion session. Those particles are subtle boundary modes, and be very explicitly identified as subtle boundary modes if the boundaries are tried. One of many ways of thinking of them. That are the symplectic partners of the soft photons of gravity. Yeah. Or you call.
Oh, yeah, I think someone over there was.
you should know the soft theorem is related to, let's say, constraint the supertranslation at characters, link the supertranslation at characters is primary. If I try to take another particle with soft, would that give us additional to constraint? Or let's say if I take another particle with soft to characteristic, would that give us, what does it do to the memory?
Yeah, so there's a lot of activity now on various questions like that, like what happens if you take multiple particles soft at once? And some things we understand, some things we don't understand. What if you take multiple particles soft at once, and that is related to sort of the geometry. That can be used to understand the geometry of the manifold of vacuum configuration.
Actually, the reception's already started. Maybe we'll just cut it there, and then we can talk more during the reception. So let's thank Andy.
Kind of flashing flood warning.
I know, that's why. Did you hear all the buzzers?
Is that what that was?
Center, we just. At first, fire.
When you got these conservation, is there some sense of we could add a conservation that breaks them all? Analogy so like what does that look like? It's a classical electromagnetism.
Yeah.